The video camera tube was a type of cathode ray tube used to capture the television image prior to the introduction of charge-coupled devices in the 1980s. Several different types of tubes were in use from the early 1930s to the 1980s. In these tubes, the cathode ray was scanned across a target which was illuminated by the scene to be broadcast. The resultant current was dependent on the brightness of the image on the target. The size of the striking ray was tiny compared to the size of the target, allowing 483 horizontal scan lines per image in the NTSC format, or 576 lines in PAL. Cathode ray tube. Any vacuum tube which operates using a focus beam of electrons, cathode rays, is known as a cathode ray tube. However, in the popular lexicon, CRT usually refers to the picture tube in a CRT television. With the introduction of the personal computer in the early 1980s, cathode ray tube became the word used for the display, which looked like a small television. It is only one of many types of cathode ray tubes. Other CRTs include the tubes used in television, oscilloscopes, or radar displays. The camera pickup tubes described in this article are also CRTs, but they display no image, and are not kinescopes. Early research. In June 1908, the scientific journal Nature published a letter in which Alan Archibald Campbell Swinton, Fellow of the Royal Society, discussed how a fully electronic television system could be realized by using cathode ray tubes as both imaging and display devices. He noted that the real difficulties lie in devising an efficient transmitter, and that it was possible that no photoelectric phenomenon at present known will provide what is required. A cathode ray tube was successfully demonstrated as a displaying device by the German professor Max Diekmann in 1906. His experimental results were published by the journal Scientific American in 1909. Campbell Swinton later expanded on his vision in a presidential address given to the Röntgen Society in November 1911. The photoelectric screen in the proposed transmitting device was a mosaic of isolated rubidium cubes. His concept for a fully electronic television system was later popularized by Hugo Gernsback as the Campbell-Swinton electronic scanning system, in the August 1915 issue of the popular magazine Electrical Experimenter. In a letter to Nature published in October 1926, Campbell-Swinton also announced the results of some, not very successful experiments he had conducted with G. M. Minchin and J. C. M. Stanton. They had attempted to generate an electrical signal by projecting an image onto a selenium-coated metal plate that was simultaneously scanned by a cathode ray beam. These experiments were conducted before March 1914, when Minchin died, but they were later repeated by two different teams in 1937, by H. Miller and J. W. Strange from ME, and by H. Iams and A. Rose from RCA. Both teams succeeded in transmitting very faint images with the original Campbell-Swinton's selenium-coated plate, but much better images were obtained when the metal plate was covered with zinc sulfide or selenide, or with aluminum or zirconium oxide treated with cesium. These experiments are the base of the future vidicon. A description of a CRT imaging device also appeared in a patent application filed by Edward Gustave Scholz in France in August 1921, and published in 1922, although a working device was not demonstrated until some years later. Image dissector. An image dissector is a camera tube that creates an electron image of a scene from photocathode emissions which pass through a scanning aperture to an anode, which serves as an electron detector. Among the first to design such a device were German inventors Max Diekmann and Rudolf Hell, who had titled their 1925 patent application Lichtelektrische Bildeleger or Fernseher. The term may apply specifically to a dissector tube employing magnetic fields to keep the electron image in focus. an element lacking in Dissector's design, and in the early dissector tubes built by American inventor Philo Farnsworth. Dissector submitted their application to the German Patent Office in April 1925, and a patent was issued in October 1927. Their experiments on the image dissector were announced in the Volume 8 of the popular magazine Discovery and in the May 1928 issue of the magazine Popular Radio. However, they never transmitted a clear and well-focused image with such a tube. In January 1927, Farnsworth applied for a patent for his television system that included a device for the conversion and dissecting of light. Its first moving image was successfully transmitted on September 7 of 1927, and a patent was issued in 1930. Farnsworth quickly made improvements to the device, among them introducing an electron multiplier made of nickel and deploying the longitudinal magnetic field in order to sharply focus the electron image. The improved device was demonstrated to the press in early September 1928. The introduction of a multipactor in October 1933 and a multi-dynode electron multiplier in 1937 made Farnsworth's image dissector the first practical version of a fully electronic imaging device for television. Unfortunately, it had very poor light sensitivity, and was therefore primarily useful only where illumination was exceptionally high. However, it was ideal for industrial applications, such as monitoring the bright interior of an industrial furnace. Due to their poor light sensitivity, image dissectors were rarely used in television broadcasting, except to scan film and other transparencies. In April 1933, Farnsworth submitted a patent application also entitled Image Dissector, but which actually detailed a quart-type camera tube. This is among the first patents to propose the use of a low-velocity scanning beam, and RCA had to buy it in order to sell image orthocon tubes to the general public. However, Farnsworth never transmitted a clear and well-focused image with such a tube. Operation: the optical system of the image dissector focuses an image onto a photocathode mounted inside a high vacuum. As light strikes the photocathode, electrons are emitted in proportion to the intensity of the light. The entire electron image is deflected, and a scanning aperture permits only those electrons emanating from a very small area of the photocathode to be captured by the detector at any given time. The output from the detector is an electric current whose magnitude is a measure of the brightness of the corresponding area of the image. The electron image is periodically deflected horizontally and vertically such that the entire image is read by the detector many times per second, producing an electrical signal that can be conveyed to a display device, such as a court monitor, to reproduce the image. The image dissector has no charge storage characteristic. The vast majority of electrons emitted by the photocathode are excluded by the scanning aperture, and thus wasted rather than being stored on a photosensitive target, as in the Icona Scope or image orthocon, which largely accounts for its low light sensitivity. Icona Scope. An Icona Scope is a camera tube that projects an image on a special charge storage plate containing a mosaic of electrically isolated photosensitive granules separated from a common plate by a thin layer of isolating material. Somewhat analogous to the human eye's retina and its arrangement of photoreceptors. Each photosensitive granule constitutes a tiny capacitor that accumulates and stores electrical charge in response to the light striking it. An electron beam periodically sweeps across the plate, effectively scanning the stored image and discharging each capacitor in turn such that the electrical output from each capacitor is proportional to the average intensity of the light striking it between each discharge event. The problem of low sensitivity to light resulting in low electrical output from transmitting or camera tubes would be solved with the introduction of charge storage technology by the Hungarian engineer Kálmán Tihanyi in the beginning of 1925. His solution was a camera tube that accumulated and stored electrical charges within the tube throughout each scanning cycle. The device was first described in a patent application he filed in Hungary in March 1926 for a television system he dubbed Radioscope, after further refinements included in a 1928 patent application. Tihanyi's patent was declared void in Great Britain in 1930, and so he applied for patents in the United States. Zwicken presented in 1923 his project for a totally electronic television system to the general manager of Westinghouse. In July 1925, Zwicken submitted a patent application titled Television System that included a charge storage plate constructed of a thin layer of isolating material sandwiched between a screen and a colloidal deposit of photoelectric material consisting of isolated globules. The following description can be read between lines 1 and 9 in page 2. The photoelectric material, such as potassium hydride, is evaporated on the aluminum oxide, or other insulating medium, and treated so as to form a colloidal deposit of potassium hydride consisting of minute globules. Each globule is very active photoelectrically and constitutes, to all intents and purposes, a minute individual photoelectric cell. Its first image was transmitted in late summer of 1925, and a patent was issued in 1928. However, the quality of the transmitted image failed to impress H.P. Davis, the general manager of Westinghouse, and Zwicken was asked to work on something useful. A patent for a television system was also filed by Zwicken in 1923. But this filing is not a definitive reference because extensive revisions were done before a patent was issued 15 years later, and the file itself was divided into two patents in 1931. The first practical Icona Scope was constructed in 1931 by Sanford Essig, when he accidentally left a silvered mica sheet in the oven too long. Upon examination with a microscope, he noticed that the silver layer had broken up into a myriad of tiny isolated silver globules. He also noticed that the tiny dimension of the silver droplets would enhance the image resolution of the Icona Scope by a quantum leap. As head of television development at Radio Corporation of America, Zwicken submitted a patent application in November 1931, and it was issued in 1935. Nevertheless, Zwicken's team was not the only engineering group working on devices that used a charge stage plate. A 405-line broadcasting service employing the Emitron began at studios in Alexandra Palace in 1936, and patents were issued in the United Kingdom in 1934 and in the USA in 1937. The Icona Scope was presented to the general public at a press conference in June 1933, and two detailed technical papers were published in September and October of the same year. Unlike the Farnsworth image dissector, the Zwicken Icona Scope was much more sensitive, useful with an illumination on the target between 4 feet C and 20 feet C. It was also easier to manufacture and produce the very clear image. The Icona Scope was the primary camera tube used by RCA Broadcasting from 1936 until 1946, when it was replaced by the image orthocon tube, Super Emitter, and image Icona Scope. The original Icona Scope was noisy, had a high ratio of interference to signal, and ultimately gave disappointing results, especially when compared to the high-definition mechanical scanning systems then becoming available. The ME team, under the supervision of Isaac Schoenberg, analyzed how the emitron produces an electronic signal and concluded that its real efficiency was only about 5% of the theoretical maximum. This is because secondary electrons released from the mosaic of the charge storage plate when the scanning beam sweeps across it may be attracted back to the positively charged mosaic, thus neutralizing many of the stored charges. Lunshinsky, Roder, and McGee realized that the best solution was to separate the photoemission function from the charge storage one, and so communicated their results to Zwickau. The new video camera tube developed by Lunshinsky, Roder and McGee in 1934 was dubbed the Super Emitter. This tube is a combination of the image dissector and the emitron. It has an efficient photocathode that transforms the seen light into an electron image. The latter is then accelerated towards a target specially prepared for the emission of secondary electrons. Each individual electron from the electron image produces several secondary electrons after reaching the target, so that an amplification effect is produced. The target is constructed of a mosaic of electrically isolated metallic granules separated from a common plate by a thin layer of isolating material, so that the positive charge resulting from the secondary emission is stored in the granules. Finally, an electron beam periodically sweeps across the target, effectively scanning the stored image, discharging each granule, and producing an electronic signal like in the Icona Scope. The Super Emitter was between 10 and 15 times more sensitive than the original Emitron and Icona Scope tubes, and, in some cases, this ratio was considerably greater. It was used for an outside broadcasting by the BBC, for the first time, on Armistice Day 1937, when the general public could watch in a television set how the king lay a wreath at the cenotaph. This was the first time that anyone could broadcast a live street scene from cameras installed on the roof of neighbor buildings. On the other hand, in 1934, Zwickau shared some patent rights with the German licensee company Telefunken. The image Icona Scope was produced as a result of the collaboration. This tube is essentially identical to the Super Emitter, but the target is constructed of a thin layer of isolating material placed on top of a conductive base. The mosaic of metallic granules is missing. The production and commercialization of the Super Emitter and image Icona Scope in Europe were not affected by the patent war between Zwickau and Farnsworth, because Diekmann and Hell had priority in Germany for the invention of the image dissector, having submitted a patent application for their Lichtelektrische Bildlegerrohre für Fernseher in Germany in 1925, 2 years before Farnsworth did the same in the United States. The image Icona Scope became the industrial standard for public broadcasting in Europe from 1936 until 1960. When it was replaced by the Vidicon and Plumicon tubes. Indeed, it was the representative of the European tradition in electronic tubes competing against the American tradition represented by the image Orthicon. The German company Hyman produced the Super Icona Scope for the 1936 Berlin Olympic Games. Later Hyman also produced and commercialized it from 1940 to 1955. Finally, the Dutch company Philips produced and commercialized the image Icona Scope and Multicon from 1952 to 1958. Operation The Super Emitter is a combination of the image dissector and the emitron. The seen image is projected onto an efficient continuous film semi-transparent photocathode that transforms the seen light into a light-emitted electron image. The latter is then accelerated via electromagnetic fields towards a target specially prepared for the emission of secondary electrons. Each individual electron from the electron image produces several secondary electrons after reaching the target, so that an amplification effect is produced, and the resulting positive charge is proportional to the integrated intensity of the seen light. The target is constructed of a mosaic of electrically isolated metallic granules separated from a common plate by a thin layer of isolating material, so that the positive charge resulting from the secondary emission is stored in the capacitor formed by the metallic granule in the common plate. Finally, an electron beam periodically sweeps across the target, effectively scanning the stored image and discharging each capacitor in turn such that the electrical output from each capacitor is proportional to the average intensity of the seen light between each discharge event. The image iconoscope is essentially identical to the Super Emitter, but the target is constructed of a thin layer of isolating material placed on top of a conductive base. The mosaic of metallic granules is missing. Therefore, secondary electrons are emitted from the surface of the isolating material when the electron image reaches the target, and the resulting positive charges are stored directly onto the surface of the isolated material.